In this video, we're going to go over how to compute the eigenvalues of a matrix. And these eigenvalues are just going to be some numbers for us. So the eigenvalues are some scalar numbers, and we're going to let lambda be our eigenvalue variable. So if we consider this matrix A down below, there's going to be a number of steps in which we use to find an eigenvalue. So I'll kind of break this into a couple steps. The step one is notice that this is a 2 by 2 matrix. So what we need to compute is the product of our scalar lambda, which is something we're still trying to find, and the 2 by 2 identity. So what we need here is the 2 by 2 identity, which is lambda times our identity matrix 1, 0, 0, 1. So this product here is just lambda, 0, 0, lambda. Hopefully that step didn't really throw you for a loop. Step 2, compute the difference of lambda I minus our original matrix A. So in this case, we have lambda I, which was what we just computed in step 1, and we're subtracting from it our original matrix A. So we have lambda, 0, 0, lambda, and we're subtracting off matrix A, which in this case is 1, minus 4, minus 2, 3. So the resulting matrix that we get is lambda minus 1, 0 minus a minus 4, which gives us a plus 4, 0 minus a minus 2, which gives us a plus 2, and finally, lambda minus 3. And the reason we wanted to compute that difference is the next step, we're going to take a determinant of that matrix difference. So I'm just going to grab that matrix and bring it along for the ride. So step 3 is compute the determinant of lambda I minus A. So in this case, we have lambda I minus A. If we take the determinant of that matrix, I'll throw these big vertical blue lines to say we're taking the determinant. We would do this like any other 2 by 2 determinant. We take the product of the main diagonal, and we subtract off the product of that reverse diagonal. So in this case, our determinant will be lambda minus 1 times lambda minus 3. We subtract off the product of that reverse diagonal, which in this case is 4 and 2, or the product of 4 and 2. And if we expand these out, we'll get lambda squared minus 4 lambda plus 3 minus 8. And doing the little bit of arithmetic left, we have this is lambda squared minus 4 lambda minus 5. So that is our determinant of that matrix we had above here. And now you might know or notice that what we're left with here is a polynomial. And for our matrix, this actually has a special name. This is called the characteristic polynomial. And its roots are the eigenvalues. So that brings us to step 5. Find the roots of the characteristic polynomial, or set the characteristic polynomial equal to 0 and find the solutions. So our characteristic polynomial in this case is lambda squared minus 4 lambda minus 5. Let's just use the quadratic formula. If we use the quadratic formula here, we have lambda is equal to minus b. So in this case, a minus minus 4 or plus 4, plus or minus the square root of b squared, which is minus 4 squared. So 16 minus 4 times a, which is the coefficient of lambda squared, which is 1, times minus 5. All over 2 times the coefficient a, which is 1. So our eigenvalues in this case are 4 plus or minus the square root of 16 plus 25, or sorry, 16 plus 20, which is 36. So doing out the remaining little bit of arithmetic we have the eigenvalues are 4 plus or minus 6 all over 2. So in other words, lambda is equal to, if we scroll back, 4 plus 6 over 2 and 4 minus 6 over 2. And of course, we shouldn't be scared of this arithmetic. This gives us 5, and this gives us minus 1. And those are our eigenvalues.